we're going to talk about Arctic plankton. Of course, to begin talking about Arctic plankton, we need to start with what the plankton is in general, what groups of plankton we know, you may know already, and then we'll show what specific features Arctic plankton, major groups of Arctic plankton hold. So let's start with plankton in general. So the term plankton, of course, is used to describe actually a group of organisms, and they all have one thing in common: they live in water, or at least in somewhat moist environment, but in water in general. And they're carried along if they live in the ocean, and we're going to focus on that group mostly. So if they live in the ocean, they are carried along by ocean currents, by water movements, without the means to swim against them. So that's the main feature that all planktonic groups have in common. But there are various groups, and plankton consists of a very diverse range of living organisms. And what they have in common is that they spend at least part of their life cycle suspended in water. It doesn't have to be a full life cycle. So this term is further divided, of course, into phytoplankton, zooplankton, which of course means plant-like organisms, and animal-like organisms, drifters, respectively. Of course, we can have many types of classification, like, for example, holoplankton. And holoplankton refers to those planktonic organisms that spend their entire life cycle as a plankton, as opposed to plankton, which is only planktonic for a part of their life cycle, and organisms that are capable, at some point of their life, are capable of resisting the currents, resisting the water movements, like for example fish. So the main groups of the plankton are phytoplankton and zooplankton, according to one major classification based on whether or not they're capable of photosynthesis. And here are some examples of most important groups. Well, that's always very subjective, but some examples of important distinctive groups of phytoplankton, for starters. So we have, for example, diatoms. Diatoms are very, very important, and they live in sort of shells, or more like houses made of glass, we might say. Actually, they're made of silica. And actually, they are the only organisms on the planet. Cell walls are made of transparent silica, so they're very interesting from that point of view. Not only from that point of view, of course. There are also these cells, these little glass houses, are decorated with very amazing combinations of different patterns. Of course, also they're the largest organisms in the phytoplankton group. Also, we have green algae or cyanobacteria, also in this group of plankton. As for zooplankton, there are various groups, and the most important one of them are crustaceans, the most important and the most numerous, I might say. And in many ways, crustaceans are analogous to the insects on land. And crustaceans, which are also a very diverse group themselves, typically they dominate zooplankton communities. And they represent a very important, a crucial link, especially in oceanic food chains. So as you can see, they're a very, very diverse group. And the term The name crustacean is derived from the shell they carry, from the shell or crust that they carry, like this external material, external jointed armor that envelopes their bodies, it protects their bodies, like external skeleton, which also means that their growth is restricted by the skeleton. So they must shed the skeleton before an individual can grow, can increase in size. And this is why typically crustaceans grow in a series of so-called molds, so shedding this external skeleton and like growing a new one. You can recognize some of those groups in the crustacean group of krill. Krill is very often associated with polar regions, truthfully, but it should be mostly associated with Antarctic region, so southern polar regions, not the northern ones. I mean, they do exist in northern polar regions, in the Arctic Ocean, but they're not that typical, and they're not the most important group of them. Actually, the most important group of the crustaceans and of the zooplankton in the entire Arctic are copepods. You can see them. You can see them here. They're not that they're not that well known, and they definitely should be. So here we can see some of the differences, some of the major differences between zooplankton and phytoplankton, and also some similarities. So both groups are mostly microscopic. It doesn't mean that all of them are microscopic. We're going to see one example of a giant zooplanktonic organism. Both groups can be found in fresh and marine water habitats, but of course one difference that is very obvious is that zooplankton is incapable of photosynthesis, so they need to feed on other organisms, and instead phytoplankton is capable of photosynthesis, so it's somewhat independent, but it also impacts where they can live and how they live, especially in Arctic habitat. And what's the Arctic habitat like? That's another important issue to address when talking about planktonic organisms. So what's it like to live in the Arctic Ocean? So the water is obviously cold, but also the temperature is, at least in the upper Arctic Ocean, is rather constant. Constant and really cold, so it's usually close to the freezing point of seawater. Of course, it's not 0 Celsius degrees. So since the Arctic Ocean is made up of salty water, of course, the temperature must reach about minus 1.8 Celsius degrees before it freezes. So temperature is usually in the upper layer like this. What about access to nutrients, which is also very important for the organisms that live there? So it's depending on the mixing of water layers, and I will show you that later. And another very distinctive feature of Arctic Ocean is limited access to light. So of course there is a polar night over the Arctic Circle, and also there is sea ice, maybe not everywhere and not the whole year round everywhere, but at some places it is, and sea ice is also limiting access of sunlight, of light to the water where those organisms like phytoplankton live. Another distinctive feature of Arctic Ocean is water stratification, so the layers. The stratifications is also quite interesting. And it is mostly sustained or fueled by the freshwater dynamics. So there is freshwater that comes to the Arctic Ocean, and the main freshwater sources are rivers. This is how the Arctic Ocean receives most of the freshwater input. Actually, it receives quite a lot of it, like about 10-11% of the global runoff, so quite a lot. So there is also rainfall and ice. There are also some low salinity waters from the Pacific Ocean through the Bering Strait. So there's a lot of going on in terms of input of water, of fresh water or low salinity water, which makes a lot of fuss. And we have, like I said, the stratification is mostly depends mostly on this input of fresh water. In general, the stratification of water depends on temperature and their salinity. So we have a so-called polar halocline. Polar halocline is a special layer of very cold water which has steep salinity gradients, and it forms below this mixed layer. So in the upper layer, we have a mixed layer where the waters mix, and below there is this barrier, a layer of very cold water, which limits actually the exchange between surface and deep ocean water masses. So there is very little of mixing in the upper layer, which also influences the way nutrients are distributed, for example. And Arctic Ocean is not a large one. I mean, comparing to other oceans, it makes around 3% of the total ocean area, but it only makes about 1% of the volume, which means that it is quite shallow. It's the shallowest of all the oceans, and it has large continental shelves. As you can see, it consists of a central basin, and there are seas surrounding it, like Barents Sea, Kara Sea, Laptev Sea, and so on and so on, Chukchi Sea, all around this central deep basin. Deep. It's not that deep. It's, like I said, it's the shallowest of all oceans. So here we can see the illustration of what I was talking about, this mixed layer, the sea ice on top of it, which also limits the access of sunlight. The mixed layer is cold, is also fresh. Then we have this halocline, so this barrier, which limits the mixing. Underneath, there is Atlantic water, which is warmer and very saline, and then there is Arctic deep water. But the mixing between the upper mixed layer, which is cold and fresh, and Atlantic water, which is warm and saline, is limited by this barrier, by this cold, stable barrier called halocline, which is stable due to salinity gradient. Like I said, it has a very it's like a saline shock for the ocean. And what does it mean for the entire group, or two main groups that we're talking about? First, focusing on phytoplankton, which is of course the very first basis of the food chain, food web in this ecosystem. It means that the primary productivity, so what the phytoplankton produces with what it has at its disposal, meaning very limited light and not that many nutrients, at least not always that much of nutrients which are necessary for primary production. It is quite interesting to notice that this productivity is not the same in the whole Arctic Ocean. So there are parts where this primary productivity is significantly higher. And you can try and compare, like here, the Arctic, the central basin looks like it's very, very productive. It's not very but productive in comparison with the other oceans, but in comparison with, like, for example, Chukchi Sea or Beaufort Sea, it is productive. You can see you need to compare the scale and the units here. So the scale here shows that it is much more productive, and the least productive is probably the Siberian Sea, I would say, based on the scale on those graphs. So it's not an uniform environment from phytoplankton. The conditions allow for some more intense productivity in some parts. Another very distinctive feature, so one was that the productivity is very different from one part of the Arctic Ocean to another, which means that the amount of phytoplankton differs significantly, and the amount of zooplankton in terms of biomass also depends heavily on what they can feed on. At least some of zooplanktonic organisms are predators, and some of them are feeding on, grazing on phytoplankton. So they need, at least the first chain in the food web, in the food chain, needs some planktonic organisms to survive. So they are clearly dependent on the amount of phytoplankton and on the intensity of primary productivity. Another very interesting feature, which of course does not only appear in the Arctic Ocean, but in the oceans in general, but is especially important here, is so-called biological pump. Biological pump, the mechanism of biological pump is explained here, and basically what should be the one thing that you remember from it is that water microorganisms really help oxygenate the Earth's atmosphere. The large amount of oxygen come not from the large forests and even Amazon forests, but from the oceans. So how do they do this? And one thing is that they, of course, planktonic organisms, phytoplankton, produces oxygen, but this oxygen needs to be transferred into the atmosphere. So they not only transfer the oxygen, but they also allow to store a lot of carbon from the ocean surface to its depth. So it's a double activity to lower the amount of CO2. So it's a pump that's, figuratively speaking, in sucking the carbon dioxide from the atmosphere and allowing it to be stored in the depth of the ocean in form of, for example, carbonates. And on the other hand, it feeds the atmosphere with oxygen. So it sounds really nice, especially in terms of first, that we all need oxygen to survive, and then that we are trying to lower and at least limit the amount of CO2 in the atmosphere, especially nowadays due to climate change we observe, and which is most likely related to the higher level of CO2 in the atmosphere. So what happens is that every spring in the northern hemisphere. The ocean surface erupts, but it erupts in a good way, in a massive bloom. It's a bloom of phytoplankton. I will show you this seasonality in a bit. So like plants, their single-celled floating organisms are phytoplankton, and they, of course, use photosynthesis. They turn light into energy, or like not to turn light energy into matter. They're, of course, they're consuming carbon dioxide and releasing oxygen during this process. But then, of course, everything dies, and phytoplankton dies as well, or is eaten by zooplankton. And those carbon-rich parts, fragments, sink. When it's dead, it sinks deeper into the ocean. And in turn, it's eaten by other creatures because nothing goes to waste in nature. So there are other creatures that live deeper in the oceans and eat those carbon-rich parts, or they just drop down and get buried in sediment, some of them. So this process is like a key to the biological carbon pump, and also is a very important part of the global carbon cycle. I don't know, you can check yourself. There's also another biological pump or that you might find interesting, also related to Arctic regions. It's so-called whale pump. In fact, you can check it yourself because that's so directly related to today's topic. I mentioned seasonality. So what happens in the northern hemisphere in the spring? So spring in the Arctic Ocean is much more intense than what we observe in, for example, in Poland. We also observe that everything is blooming, everything is coming back to life, but in the Arctic, it's like another level of blooming. So first, you need to understand that the sunlight appears, and if the sunlight appears after a long polar night, of course, it doesn't last exactly the same number of months in every part of Arctic Ocean. Sometimes it's shorter, sometimes it only lasts 6 months on the very top, so on the North Pole or around North Pole, but in other parts it's not that long, but still there is a prolonged period without any sunlight. So the polar night ends and the sunlight comes back and the ice melts. And the ice melting is not only allowing more sunlight to reach this upper layer of the ocean. So when this thaw of this ice melting begins, there were also a lot of organisms trapped in the ice, in the sea ice, while it was formed the previous, let's say, previous autumn. So a lot of them were trapped. Of course, they're dead matter now, but they're a very rich source of nutrients. So it's like a fertilizer. It's like adding a fertilizer to this water that suddenly has a lot of light. So then what we observe in an absolute life explosion. It's an explosion because it's very intense, but it's also an explosion because it's very, very short but prolific. So the primary production that I showed you, which is of course different in different parts of the Arctic Ocean, is very, very intense and very, very short. And it starts in some parts it starts earlier, in some parts it starts a little bit later. So it's the bloom period arrives first in the Barents Sea, which is the beginning of April. And in the North Pole, for example, it's August. So there is only spring in August, in some short period of time in the North Pole. But you can observe this little tail that follows this very short and very intense prolific bloom period. And there is no tail in the North Pole area, but there's quite a long tail in the Barents Sea. And it's very, very interesting to observe that in some parts there's also some summer and autumn production, but only in some parts. But this production is nothing like this first bloom of life. And then after the summer ends, and the summer is, also a subjective term in the Arctic, because we have, like I said, in the North Pole, there's a short spring in August, but around August, September by the latest, the production, let's say August, the production is actually declining. There are occasional blooms sometimes, and there is a very fast decline. And then the darkness comes back. During the polar night, planktonic algae, the plankton, phytoplankton, stops growing at all. When there is polar night, there is no chance for any photosynthesis because of the lack of light. And of course, there are no or little nutrients available as well, but without light, it's like the first and primary limiting factor. So this was a second very important feature of the Arctic, especially related to the phytoplankton. And the third one, I will just explain very, very shortly. Third one is to maybe notice and try to remember is so-called DMA and CLO. This sounds pretty mysterious, but I will just explain in a minute. So DMS is a chemical substance, it's a dimethyl sulfide, simply. And it is produced by phytoplankton, some types of phytoplankton, and generally it's produced in low concentrations and really generally harmless. And actually you can, I believe, even if you never heard about DMS, it should be DMS here, by the way, you must have smelled it if you were ever at the seaside. It's like a slightly unpleasant odor. And when you're like cooking corn or cooking cabbage, it's like this slightly unpleasant scent of it. So that's DMS. So it's produced naturally, it's harmless. And what is observed, and what was observed by four authors, four researchers, Charlson, Lovelock, Andre, and Warren, thus the CLAW abbreviation, so another mystery solved. And what they observed, that DMS might have some effect on cloud formation. So if there is a lot of this bloom of phytoplankton and there are a lot of production of DMS, so the DMS concentrations in the Arctic continue to rise. And actually it could change the patterns of cloud formation in the Arctic. And why is it interesting that it is, first of all, it's only a hypothesis. The CLAW hypothesis is only a hypothesis, and we don't know exactly how strong this impact is, so how it influences this cloud formation. And why is it interesting? It's interesting because usually when we talk about climate change, we talked about positive feedback loops. So, for example, it's very, due to climate change, it's very hot in the summer. If it's very hot in the summer, people tend to use a lot of air conditioning. If they use a lot of air conditioning, they use a lot of electricity. If they use a lot of electricity, it means more CO2 is produced for the production of this electricity in most cases. And so this is like a vicious circle. So the effect only pumps up the cause. But in this case, it's one of the rare examples of so-called negative feedback loops. So it seems like, okay, it's warmer, so blooms of phytoplankton tend to be more intense. Some say so. But on the other hand, the more DMS is produced and the cloud formation is more intense, and clouds protect this area, at least this area, from direct sunlight. And it means that the sunlight input is limited, so the photosynthesis would be limited as well, and it would be a self-limiting mechanism. It's not It's not entirely understood by researchers, and like I said, the scale of it, maybe it's just a small scale and a local scale, but still an interesting mechanism to observe. So I guess I don't have to convince you anymore that those tiny organisms are of a very huge importance. So that, like I said, primary production, oxygen production, actually the number is 80%. 80% of global oxygen production comes from the oceans in general. And so they're that important, even though they're so tiny. And I mentioned that they need to remain close to sunlight because, of course, phytoplankton needs to remain close to sunlight because it needs sunlight to survive for photosynthesis. But it also shows how perfectly those organisms are adapted to stay close to the sunlight, stay in the upper zone of the ocean because of their shape. Their shape allows them to sink very slow. Of course, when they're dead, I mentioned they do sink, which is also a good thing because it allows us to give a kick to this biological pump. Then we have only a couple of minutes for the particularities and the importance of the zooplankton. Okay, so I just focus on the most important organism that is little known, and this is why I started with not very focusing on krill, which might be the first thing that pops to your mind when you think, okay, zooplankton in the Arctic. Krill is the most important also source of food for many organisms, but in the south. In the north, there's only one king of the Arctic, and I'm sorry, that's not a polar bear. It's actually Calanus glacialis. It's a species, and it's a species that is, as you can see, not very, it looks not very epic, maybe, but it is essential in the whole marine ecosystem. And what it looks like, it has a very, very tiny body, like size of, and also looks like a grain of rice. It has little legs, and sometimes they have a very well developed eye, like a telescopic eye. Actually, that's a description not only of this Calanus glacialis species, but of the whole group, copepods that I mentioned, that are the most important group of crustaceans in the Arctic, at least. So in general, copepods can be like blue, red, transparent, luminescent. They can be benthic, they can be pelagic. They do not only live in polar regions. They can also be observed in tropical regions. But some people maintain that copepods in general are the most numerous animals in our planet. They can be found in all seas. They have developed numerous strategies to survive, so not bad for an animal, zooplanktonic animal, which is that big, like a rice grain. And the most important thing is that the copepods represent like crucial interface between phytoplankton that we described before and the fish. So they're a crucial link in this Arctic, especially in the Arctic food chain or food web. And why Calanus glacialis specifically is the most numerous and the most important species, specifically in the Arctic ocean. So the whole delicate balance of the food chain depends heavily on this one, Calanus glacialis species. It's not a predator. It's a herbivorous zooplankton species, and it's specifically adapted to melting sea ice and this blooming that we observed, that we started with. Blooming of a few small algal phytoplankton species. And so what happens in this, why is it so important? What happens in this Arctic food chain is that the most important nutritional compound are the omega-3 fatty acids. You may have heard of them. There's like described as superfood. Even for people, it's not that simple, but they're like a superfood, omega-3 fatty acids. And they're produced exclusively, here they're produced exclusively by some phytoplankton, by some marine algae. But by phytoplankton, but also in the sea ice. That's not that important. So Calanus glacialis, this little fellow, grazes on this algae, and so it absorbs those omega-3 fatty acids. So they're already in the system. It not only absorbs them, but it can also store them. It has these structures, so-called lipid sac, that they can take up to 40% of the whole body volume. So they can store a lot of fat. It allows them to float, but also it's like food for them, right? It has to store this large amount of fat, of lipids, to survive the long Arctic winters. So, like I said, in the winter there's no phytoplankton, no photosynthesis whatsoever, but they need to survive somehow, so they have those sacs full of lipids. It's like some say it's even up to 70% of its body mass when it's stored for the long winter. So from the point of view of fish, especially Arctic cod, this is like a perfect source of food. So this is like very fatty, lipid rich. So plankton is like a primary food source, not only for Arctic cod, but also for many marine birds, also for many whales. And of course, the fish, the Arctic cod, is like the main course for seals, and the seals are the favorite meal of polar bears. So this is how we meet the other king of the Arctic, as you see. It all starts with photosynthesis, of course, but the polar bear wouldn't be able to survive without this little one on the left. So, because the Calanus glacialis sort of puts it in the system, puts this crucial compound in the system, those omega-3 fatty acids. So it was really short about the zooplankton, but I also because I want to focus more on the role that they have and how maybe let's end with how this change of climate that we also mentioned, the climate change of general conditions in the Arctic in particular, can affect phytoplankton and thus zooplankton, because they're all zooplankton relies heavily on the phytoplankton. So, like I said, Calanus glacialis is perfectly adapted to the environment as it is, but not, and it can also adapt quite fast to the changing environment. But not all the species can adapt so quickly. So if now we have, especially in the Arctic, we observe climate change, which means that ice melting is faster and starts earlier. It can have various consequences, and one of them is probably, in some cases, or at least in some regions, not that much omega-3 fatty acids can be produced, because if the ice is melting, it's like too much ultraviolet reaches the water, and in some cases phytoplankton can bloom, but is not so efficient in producing those omega-3 fatty acids. This can affect Calanus glacialis, but Calanus glacialis, will survive. They will be just less numerous. But for this less numerous and lower biomass of Calanus glacialis means a catastrophe for the whole food chain, which really is endangered. So, as usual, the disruption of cycle causes a serious mismatch, like here. So currently it should be perfectly arranged and synchronized. So the ice melt, the bloom, Calanus glacialis grazing, a lot of food available for not only for fish, but for example, for little auk, like I said, some marine birds that really need this at this time because they're at this point in spring they lay eggs and then they feed their the young birds, right? But in this mismatch scenario, uh, too much happens too early and the marine birds are not able to adapt as quickly as a small organism. So they do not have enough food and their weight is lower, their survival rate is lower. So this disruption, this change which causes that those processes are not as well synchronized is very dangerous, one of the most dangerous consequences of the climate change. And I mentioned a negative feedback loop earlier with this DMS and claw hypothesis with cloud formation. Here we have a very clear example of positive feedback loop, which means if we have strong blooms of phytoplankton, even if they arrive early, too early from the point of view of marine birds like little auk. We have more chlorophyll. That means that at least you have more phytoplankton. It means we have more chlorophyll, which at least at some point means that we have decreased albedo, which means that not as much of sunlight is reflected by the water. The water is darker and it absorbs more of the sunlight. Okay, from the point of view of photosynthesis, at the beginning it seems great, but because there is more solar energy available, but it means that temperatures rise and again more blooms and more decreased albedo and more energy absorbed. At some point it leads to, for example, less omega-3 fatty acids produced because there's just too much UV light and so on. And this is a perfect example of a positive feedback loop, which is very, very common in the processes related to climate change, affecting both phytoplankton and as a result, mostly the zooplankton. So that's all I had to say. Thank you for listening.